Hello everyone, welcome to this video. In this video we shall see how to trace a simple Cartesian curve. So most of the time we know how to trace some standard curves. For example, you know how to trace this curve. Obviously you know this is a straight line passing through origin having an angle of 45 degrees with the x-axis. Similarly, there are many other graphs which you know how to trace or how to plot. So we have this e to the power minus x graph. So this is, again, we know what is this graph. So, but what if I have some implicit relationship between x and y? For example, this y cube is equal to x cube plus ax square. So now this is an implicit relationship between x and y, and such a curve is not so easy to draw, right? So this is not so easy to draw. So what could be done? There are various tools in mathematics with which you can draw such curves. So what we do in effect is that we try to gain certain information from this curve and we just join those points of information together and we have the complete information about this particular curve. So let us get started for this particular curve. Here, the first point that we shall see about this curve is what is the domain and range for this particular function. And particularly we are interested in calculating what is this y for various values of x. So for that, firstly let us see what is the value of y. So we have y cube as equal to x square multiplied by x plus a. I can write my given curve to be in this form. So I can now take the cube root on both sides. So I'll be having x raised to power 1 by 3 whole square, and then I would have x plus a raised to power 1 by 3. So now you see, this term being a square of some term, this is always positive. So here the sign of this term would be affected by the sign of this term. So in effect you can say whenever this x plus a is negative, you have y as negative. So that means whenever x is less than minus a, you would have y as less than 0. So that means in this interval minus infinity to minus a, we have our curve would lie below x-axis. Our curve would lie below x-axis. So this much information is available to us. So whenever we are in this interval minus say minus infinity to minus a, here our curve would be below x-axis. So this is known to us. Next thing, let us see the case when this x plus a is greater than 0. So this would imply, if this is positive, so that means this could also be positive, right? So y would be positive. So that means whenever x is greater than minus a, it implies y is greater than 0. So that means whenever we are in this interval minus a to infinity, our curve would lie above x-axis. So in this case, say this is the point minus a and minus infinity, so our curve would lie in this particular region. So this information is obtained from this point. Again, let us see another set of information. So let us now discuss the symmetry of this function. In order to check the symmetry of this function about y-axis, so let us first check its symmetry about y-axis. What we do, we just change or we just replace x with the corresponding minus x. So what do we get? Our curve was y cube is equal to x cube plus ax square, right? Now if we replace this x with minus x, so we would be having minus x whole cube plus a into minus x whole square. So it would be minus x cube plus ax square. So we have y cube is equal to minus x cube plus ax square. So now this quantity is not the same as the given curve. Now because they are not equal, so that means the given curve was, say, equation number 1. So therefore we do not have any symmetry about y-axis. So there does not exist any symmetry about y-axis. So we'll check the same thing for x-axis. For x-axis, what we do instead is we just replace y with minus y. So when you replace y with minus y in your equation 1, we would have minus y cube, that would be equal to x cube plus ax square. So when you simplify this, you will be having minus y cube the minus y cube is equal to x cube plus ax square. So which is again not equal to equation number 1, the given equation. So which is again not equal to 1. So therefore we do not have any symmetry about x-axis as well. So now if there is no symmetry about y-axis, no symmetry about x-axis, so obviously there would not be any symmetry. Therefore no symmetry exists about origin as well. So this information is obtained. We do not have any kind of symmetry. The graph of this curve would be different for all these different quadrants, right? So let us next see whether our curve passes through origin or not. So let us see whether our curve passes through origin or not. For that, we just check whether the point 0, 0 is satisfying this curve or not. So when you substitute this point in the equation number 1, that means the given curve, you would have the left hand side to be y cube, which would be 0 cube, that would be 0, and the right hand side would be x cube plus ax square. So this becomes 0 cube plus a into 0 square, so that would simply be 0. So obviously this left hand side and right hand side, they are equal, so that means the point 0 is satisfying this curve. So therefore we can say the curve given by equation 1 passes through origin. And similar to that, we can also check at which points does this graph, at what points does this graph intersects x-axis. So we know the graph would intersect x-axis when y is 0. So when y is 0, your curve would become 0 cube is equal to x cube plus ax square, or you would have 0 is equal to x square into x plus a. So this implies either x square is 0 or x plus a is equal to 0. So this implies either x is 0 or x is equal to minus a. So the points of intersection of this curve and x-axis, they are, one is 0, 0, that we already have, and one point is minus a comma 0. So this is the additional point that we got in addition to this point origin. So let us now check at what points does this graph intersects y-axis. So for that, we just put x as equal to 0 in the given curve. So we have y cube is equal to 0 cube plus a into 0 square. So this implies y cube would be 0, or in other words y is equal to 0. So the point here is origin only. So no additional point is obtained from this side. Next, we examine the tangents for this particular curve. So for evaluating or for calculating the equation of tangent, what we do, we just equate the lower degree terms. We just equate the lower degree terms in the given equation to 0. So our equation was y cube is equal to x cube plus ax square. Now you see the degree for this particular term, that is equal to 3. For this particular term it is 3, and for this particular term it is 2. So this is the lowest degree term available to us. So that means we will equate this term as equal to 0. So this would give you x square is equal to 0, or you could write it to be x is equal to 0 and x is equal to 0. So that means we obtain two tangents at 0, 0. Moreover, these two tangents, they are real. We obtain two tangents at 0, 0, and these are real and coincident. If they are real and they lie on each other, so that means we would have a cusp at this point. So now what is this cusp? The cusp has a shape like this, where this is the point where we are talking about the cusp, and because here this is a multiple point, and in fact it would be a double point because the two branches of the given curve is passing through this particular point. One branch is this one and one is this one, right? And moreover, these two branches, they would have the same tangent available with it, right? So we have the same real and coincident tangent available at this particular point for this particular curve. So we obtain a cusp at this particular point. So thereafter, let us evaluate the asymptotes. What is an asymptote? Asymptote is basically, it is a straight line such that whenever the curve tends towards infinity, the distance between this curve and the line goes to 0. The distance between this straight line and the given curve goes to 0. So that is the definition for asymptote. Now in order to see what asymptotes does this curve have, we first check for horizontal asymptotes. So for this, in order to calculate the horizontal asymptote of the given curve, what we do, we just equate the coefficient of highest degree term, in x to 0. So what we are doing, our curve was x cube plus ax square is equal to y cube. This was the given curve. So now what we are doing, we are taking the highest degree term in x. So highest degree term in x is this one, and its coefficient is equal to 1. So we are just equating the coefficient equal to 0. Now 1 is equal to 0. This thing is not possible. If this thing is not possible, that means there does not exist any horizontal asymptote to this curve. So next we examine whether there are any vertical asymptotes. So for that, what we do, we now equate the coefficients of highest degree term in y to 0. So we just equate the coefficient of the highest degree term in y to 0. So that means the highest degree term in y is this one, y cube, and its coefficient is again equal to 1, so this is equal to 0. Now this thing is again not possible, therefore we also do not have any vertical asymptotes. So no vertical asymptotes exist. So next thing that is remaining here is to check for oblique asymptotes. Oblique asymptotes are those which are not parallel to x-axis or y-axis. So they would be having something like this. Their equation would be something like this: y is equal to mx plus c kind, where what is this m? M is the slope of that line and c is the corresponding intercept. So here we are interested to calculate what is this m and what is this c. So for that we have certain formula. What is that formula? It says that if you have the degree of the given curve, if that is given to be n, so in that case what we do, we construct two polynomials. One is phi n minus 1 as containing all the terms with degree n and all the terms with degree n minus 1 . So this is what we do. Let us see what would be in our case. So in our case n is 3 because our curve is y cube is equal to x cube plus ax square. So maximum degree here is 3. So we have n is equal to 3. And moreover, we construct this phi 3 of x and y. Phi 3 of x and y would be all the terms having degree 3. So all the terms having degree 3 here would be y cube minus x cube. So you could shift all the terms to the left hand side. So you would have y cube minus x cube minus ax square is equal to 0. So the terms with degree 3 are y cube minus x cube. And what would be phi 2 of xy? So that would simply be all the terms having degree 2. So it would be minus ax square. Now what we are going to do, we will put x is equal to 1 and y is equal to m into this equation. So we would have phi 3 of m as m cube minus 1. And here we would have minus a, right? We would have minus a. Phi 2 of m is minus a. So now in order to calculate what is m, we substitute this phi 3m as equal to 0. So that means we would have m cube minus 1 is equal to 0, or m cube is equal to 1, or we would have m is equal to 1. So now the value of slope is equal to 1. So c would simply be obtained using this formula, minus phi n minus 1 of m divided by phi dash n of m. This is the general formula. N in our case is 3. So we would have c to be minus phi 2 of m divided by phi dash 3 of m. So we have phi 3 of m. So phi 3 dash, that means the derivative of this term would be 3m square, right? So it would be minus 3m square divided by, so I'm sorry, this is the value of phi 3 dash m, right? So it would be 3m square, and minus for phi 2m is minus of a, right? And the moreover, the value of m is equal to v1, so we have c as equal to be a by 3. We just substitute m is equal to 1 over here. So we have c as a by 3, m is 1, so our oblique asymptote is 1 into x plus a by 3. So our equation is y is equal to x plus a by 3. So this is the oblique asymptote that we have for the given curve. Right, so this is all about asymptotes. Next, let us see what are the intervals in which the given curve increases or decreases. So next, let us examine in what intervals does the given curve increases or decreases. So in what interval, fifth point is interval of increasing and decreasing function. So for that, what we do, we just evaluate the first derivative of this curve y. Our curve was y was x raised to power 2 by 3, and then we had x plus a raised to power 1 by 3. So this was the given curve. So now in order to find dy by dx, we just differentiate this curve with respect to x. So here there are two terms in multiplication, so we would apply this product rule of differentiation. So first function as such, then the derivative of second term, it would be 1 by 3 x plus a raised to power minus 2 by 3, and then the derivative of first term, it would be 2 by 3 x raised to power minus 1 by 3, and then the second term as such. So we can very easily simplify this. So let us see what do we have after simplification. So when you simplify this, you would have dy by dx that is equal to x plus 2a by 3 divided by x plus a raised to power 1 by 3 whole square, and then x raised to power 1 by 3. So this is what we obtain after simplification. So now you see here, the sign for this term is always positive because this is the square of some term. So whatever is inside, it will be squared, so it would be positive. So that means the sign of dy by dx that only depends upon the sign of these two terms. So for increasing and decreasing function, we have this result that whenever dy by dx is greater than 0, we have the interval for increasing. So in that particular interval, our function is an increasing function, and whenever dy by dx is less than 0, in that particular interval, our function is decreasing function, right? And whenever dy upon dx is equal to 0, there we do not have any increasing or decreasing function, and there the slope of the function is 0 and the function is treated as constant over there. So now in this first case, in order for this derivative to be positive, either both these terms should be positive or both these terms should be negative. So let us see this case. So the first term is either x plus 2a by 3 should be positive, along with x raised to power 1 by 3, this should also be positive. This is one case. And second case is x plus 2a by 3 either this should be negative along with x raised to power 1 by 3, this should be negative. So when you solve this one, you would have x greater than minus 2a upon 3 and x positive. So that means when you see this on the real line, you have 0 here, minus 2a by 3 is somewhere here. Now you are saying x is greater than this quantity, so that means x would be somewhere here, and in this case we are saying x is greater than 0, so the common portion is this one. So our interval in this case becomes 0 to infinity, and in the second case our interval becomes x is less than minus 2a upon 3 and x is less than 0. So when you see this on the real line, we have 0 here, say minus 2a upon 3 is here, x is less than this quantity means x is somewhere here, and x is less than 0 means x is somewhere here. And when you see the common portion, this is the common portion that you have. So that means our interval here is minus infinity to minus 2a upon 3. So overall, our function is an increasing function in the interval minus infinity to minus 2a upon 3 union with this interval 0 to infinity. So 0 to infinity. So here our function is an increasing function. So now let us see the second case. In the second case, we have dy upon dx to be less than 0 for it to be a decreasing function. So for this to be a decreasing function, the sign of these two terms, that should be opposite sign. So that means whenever x plus 2a by 3 is positive, that means x raised to power 1 by 3 should be negative. Or in other case, we have x plus 2a upon 3 to be negative, and simultaneously x raised to power 1 by 3 should be positive. So these two cases are possible whenever your derivative is less than 0, is negative quantity. So when you solve this one, you would have x greater than minus 2a upon 3 and x less than 0. So that means whenever you have some real line, 0 over here, minus 2a upon 3. So when x is greater than minus 2a upon 3, so that means we are saying x is somewhere here. And when your x is less than 0, so that means your x is somewhere here. So the common portion here is this one. So our interval here is minus 2a upon 3 to 0. In the second case, we have x less than minus 2a upon 3 and x greater than 0. So now here, when you see the real line, this is the point 0, this is the point minus 2a upon 3, x less than minus 2a upon 3 means we are here, and x greater than 0 means we are here. So there is no common portion satisfying these two regions simultaneously with an AND condition, so no interval is obtained here, right? So the only interval is this one where we have a function to be the decreasing function. So let us see what do we have. We are saying this is a real line, this is the point 0, this is some point minus 2a upon 3, and we are saying within this interval minus 2a upon 3 to 0, our function is an decreasing function. So here the function is decreasing and here the function is increasing. In this interval minus infinity to minus 2a upon 3, and in this interval our function is again an increasing function. So here that means the derivative of our function f dash of x and y has the quantity positive, negative and positive. Moreover, when you see this dy upon dx to be equal to 0, when you check dy upon dx to be 0, when you substitute this equal to 0, you would only have x plus 2a upon 3 equal to 0. So that means you would have x value to be minus 2a upon 3. That means the likely maximum or minimum value is obtained at this point. So let us check whether do we have a maxima, do we have a maximum value or we have a minimum value at this point. So how can you check this? You can either take the double derivative and check what is the sign of this double derivative at this particular point. If it is positive, then you would have a minimum, and if it is negative, then you would have a maximum over there. Another shortcut method to check whether at this point we have a maximum or a minimum, what we can do, we can check the sign of this. So we are saying our function increases in this interval, then decreases, and then increases. So likely at this particular point we would have some maximum value. So it is obvious by having a look at this value. So here we would have at this point a maximum value of the function. So this is okay. So now next let us determine how the curve behaves within these intervals. So that means we are going to check the nature of the curve in this particular interval. So let us see it. Next is the concave upwards and concave downwards. In order to check this behavior, what we shall do, we shall see the double derivative of the given curve. So we had the first derivative with us. Now we can check its double derivative. You could just differentiate the term, and we had dy upon dx as equal to x plus 2a by 3 divided by x plus a whole square into x raised to power 1 by 3. So now when you apply the quotient rule onto this, and when you simplify this a bit, you would have the double derivative, and it comes out to be minus 2a square divided by 9 into x plus a raised to power 5 by 3, and then you have x raised to power 4 by 3. So now here you see this term would always be positive, no problem in that. This term could also be written as x raised to power 2 by 3 square. So that means this would also be positive, right? And this is constant, makes no difference. So that means the sign of this d2y by dx2 is determined from the sign of this particular term. So what we can do, if d2y by dx2 has to be positive, one negative sign is there, so this term has to be negative. So that negative and negative makes d2y by dx2 as positive. So that means here we should have x plus a to be negative. And this is the condition when your second derivative is greater than 0. So this condition corresponds to concave upward nature of the curve. So that means your curve would something be like this. And you can say this curve can hold water into it, right? So what does this mean? It means x is strictly less than minus a. So our interval here is minus infinity to minus a. So in this interval your curve is concave upward. So let us see the second case. In second case, this second derivative is strictly less than 0. This is strictly less than 0 when this quantity is positive. If this is positive, we have a negative sign over here, so that overall we have a negative sign. So we have x plus a to be positive in this case, so that d2y by dx2 becomes negative. This is the condition for concave downwards. So here if this is true, that means your curve would something be like this. So it won't be able to hold any water into it. So here the interval would be x would be strictly greater than minus a. So that means your interval becomes minus a to infinity. So in this particular interval, your curve is concave downwards. Moreover, at this point, minus a, your curve changes behavior. So before it was concave upwards, and after that it is concave downwards. That means at this particular point, at x is equal to minus a, we have the curve has a point of inflection. Right? So this information is enough for us to draw the graph of the given curve. So what do we have until now? If this is minus 2a upon 3, so we would have minus a somewhere here. So we say in this particular region, we have concave up nature of the graph, and from here to here we have concave downwards nature of the graph. So that means with all this information, let us try and draw the graph. So when we draw its graph, we would have our y-axis and then we would have our x-axis, right? So this is our y-axis, say this is our x-axis, and we have this point 0 over here. Our curve passes through this point, this is the origin, this is x-axis and this is y-axis, and then we also know our curve passes through, say this is point minus a, our curve passes through this point minus a comma 0 as well. So these were the 2 points from where our curve was, our curve passes, right? Moreover, we know what is the graph for y is equal to x. It is something like this, a straight line passing through origin, right? So, but our asymptote here is not this line, but a translate of this line. So that means our asymptote is y is equal to x plus a upon 3. This information we have just evaluated in the results for asymptote point, under this asymptote point. So this was our asymptote. So now if this is minus a, this point would be minus 2a upon 3, and say this point would be minus a upon 3. So this curve has been translated from this curve by the unit a by 3 towards the left hand side. So we would have our curve to be our asymptote. This is usually represented by a dotted line. So it would be something, wait, so it would be like this. So our asymptote would something be like this, y is equal to x plus a by 3. So now we would have to make this curve. So remember that within this interval from minus infinity to minus 2a, our curve is strictly increasing, and then it is decreasing, and then it is increasing. So what would be our curve like? And moreover, it is passing through these 2 points from minus a to 0. From minus a to 0, the nature of curve is concave downwards. So it would be something like this. So it would be something like this. And then at this point, we also have cusp with us. So that means if your curve is coming like this here, so it would be like this. Moreover, we have asymptote by this line, y is equal to x plus a by 3. So it would something be like this. It would tend, whenever this curve and this line would go to infinity, the distance between them will tend to infinity, will tend to 0. Right? And what about the left hand side of minus a? From the left hand side of this minus a, our curve is decreasing, and moreover it is concave downwards. So if this is concave downwards, so it would be something like this. So we would follow this asymptote line, right? So it would be something like this. And it will meet at this point, this curve. So our curve finally looks like this. So, and moreover, this point would be the point of inflection. So this is how, after getting so much information about the curve through various tools and techniques, we were able to finally draw this particular curve. So what we did is, we just firstly saw what was the domain and range of this particular function. So accordingly, our function lie in this particular range, right? It is something like this, right? So this thing is true. Then under second point, we saw the symmetry. We saw there is no symmetry in the curve. Then we saw the curve passes through origin. Moreover, it intersects the x-axis at these 2 points, and with the y-axis with only the origin. And then we saw the tangents corresponding to these points. The tangents here corresponds to x is equal to 0 and x is equal to 0. So we have real and consonant tangents. So we found the cusp at this particular point. Then we saw the asymptotes to this curve. There were no horizontal and vertical asymptotes, whereas we had oblique asymptotes. So we find out what is the value of m and c using the formula. So we obtain the asymptote as the line y is equal to x plus a by 3. This was the oblique asymptote. Next, we saw the intervals for increasing and decreasing functions. For that, we differentiated our given curve with respect to x, and then we saw what is the sign of this derivative, and in which interval it is increasing and in which interval it is decreasing. So we found those intervals in which it was decreasing and it was increasing, and then we saw the signs of this double derivative, and we concluded the intervals for concave upwards and concave downwards. And moreover, we found the point of inflection as well. At x is equal to minus a, we had this point of inflection. So with all this information, we draw this curve, and it comes out to be like a very nice looking curve like this. So I hope you understood this concept in question real well. So that is it for this video. Thank you for watching.